Continuing our discussion of dehydration of alcohols, we're going to do the dehydration of vicinal diols. Vicinal diols are also known as glycols. Vicinal being adjacent carbon. And I forgot to show the water, didn't I? In both reactions, I hope you see a rearrangement. Which atom rearranged to make this product where the O is still on this carbon, but a methyl has, well, I think I know the answer. A methyl has moved. It's right there. This one, I hope it's obvious an H moved, although it might not be obvious because stick figures don't show H's. Are there any H's on this carbon here? No. There's an H on the same carbon there. So it looks like you lose one of the O's. Okay. Now, which O do you want to lose first? Based on our last activity, and I just want to base it on this one little fact. This guy that made a carbocation that wasn't even very good, like secondary is about the minimum you have to get a cation, required that triangle. Anything with a less stable cation is slower, and you don't get a cation if it's primary or methyl. So using that information from a previous mechanism, tell me which of these alcohols will dehydrate faster. The one on the right, which can give a nice tertiary carbocation. So I want your mechanism to reflect this knowledge that you just reflected to me verbally. You better be dehydrating the one on the right faster than the one on the left. So if I had to circle a major product, I would circle the one that comes from this O disappearing, and I suspect that's this product here, right? You might as well go ahead and circle it if that was part of your question. Your explanation might not be the one you expect, though. So I'm getting rid of the O on the right for my major. So on a test, I might say this, mech for both, circle major, and you know me, explain. I know that's your least favorite part. Here we go. We got to protonate it out. Hey, what was the purpose of protonating that alcohol? To make it a good leaving group. Even better, we made it an excellent leaving group. And what would be your next guess for something to do based on your answer you just gave me? Make it leave. Nice answer. You get a nice carbocation that's tertiary. Tertiary C+, right? Mm-hmm. Up until this day, you thought that was the best carbocation you could make. Up until today, based on what you've known before today, you'd say that is the best cation in this course for carbon. You're about to learn something even more important than hyperconjugation. And it's called conjugation. Oh. If I told you conjugation is synonymous with resonance, you'd say, maybe you'd say, maybe not. Secondary C+, that can, oh, why do you think I drew those lone pairs there? Oh, I didn't draw the C+. I got a free keyboard too. There you go. Why is that cation so much more stable than the one to the left? And if you say hyperconjugation, I'm just saying no. It's less stable based on hyperconjugation, but there's something more important than hyperconjugation. they can resonate and make a full octet species. That's your whole answer, by the way. If you got something with full octets, it's always more stable than something with an octet violation. How's that for a good generalization? Yeah. Oh, this arrow needs to change. Look, what kind of arrow is that? Resonance arrow. And you guys tell me how that becomes that. And I will remind you, when you made this oxonium, you also made HO3 SO minus. I'm consistent. I only remember it when I need it. That's why I'm showing it now. And the cat saying meow. And I'm going to show you how you can save a little time. I think a lot of us in this room were surprised about resonance on our last test. Took you by surprise. Resonance in a species where it can happen is happening. There's almost zero activation energy for this. So as soon as you get this cation, now this process starts happening millions of times per second. Okay? So in our allylic radicals on our last test, that was what I wanted you to look at. And then pick the product with the more stable CI bond. That's beside the point. Not relevant here. This is a much better resonance form because it has full octets. And it goes to this. You can combine a resonance step in a mechanism with either the previous step or the next step. And that saves you time. You could have gone from here to the final product and saved drawing this intermediate. I will show you right now. So instead of doing that step separately, I'm just copying this species here. Oh, make it in green at least. And you can show that going to the product with using your base HO3 SO minus, and you can probably guess the arrows. Forget about using the resonance. Don't need to. Your mechanism is going to have resonance in it, and it's going to look a lot like a tautomerization. Watch. What does the base always grab in a tautomerization? A hydrogen. What happens to the bond from that hydrogen to the atom it used to be bonded to? It becomes what kind of bond? Pi. That is just like tautomerization, except this one stops here. It's over. The other one had one or two more arrows. And that's it. So you see how you do have the resonance in this arrow here, don't you? It's there. Here you resonated a lone pair and then deprotonated. Here you're deprotonating and resonating the sigma. And there you go. So let's just do this version for the other product. So it's a big mechanism. I need to realize that the other product came from a different rearrangement. And I need to look at my reactants before I figure out what rearranged again, because we already verbally said what rearranged to get from here to here. Well, we clearly lost this O to make a cation here. Not as nice a cation, so definitely a minor product. And you better move your methyl after you make the cation. And then we're going to do the cation elimination here. It's like E1. If you look at this one, like E1 in quotes. That's the carbocation, right? And you're grabbing an H from an adjacent position. Put it in quotes. You're going to need a second copy of the reactant for the other product, because you need to get rid of the other O. Starts off the same. So you're going to remind me what's the purpose of doing this first step? Bless you. What's the purpose of doing this first step? Making a good leaving group. Bless you. And it does the same thing. Secondary, you're allowed to go to cation. And you can show off. What did you say had to move to get to this product here? I need a light pink or something that's not too obtrusive. I think I can get to the final answer. What has to move? A methyl. Are we okay with that? That will move the methyl over. What's next? I'm going to combine. That's going to make a cation here, right? Like there's a cation here. What are you going to do after you've got the methyl over there and a cation on this card? Remove the H with my cat. So I got my cat, HO, 3SO minus. I'll write it right here. That's where I made it. Grabbing H. The resonance forces the methyl over. Wow, that says what happens. This is probably more realistic. Yeah. I think as the methyl starts moving, the carbon starts feeling positive, and then this elimination happens. This is probably a little more accurate. Yeah. But if you're having trouble seeing it, do you want the version where it's step by step, nothing combined? Just to see if you like the other one better? I think it's a good idea. So we can take it from here. I'll take it from there and I'll do step by step because a lot of students, they prefer it that way. I'll do the rearrangement first. Show the result. Nice result. Resonating cation, right? And then that's going to join up with the pink arrow above. Because you're going to use your OSO3H minus. And grab the H. Sigma becomes pi, end of story. I didn't combine anything down there. Okay. And we'll do a big one with a ring. And I'm pretty sure you guys are going to make me do one on Wednesday. For sure. You're going to find on the last 4 or 5 tests. And it's official now. I'm gonna put it in writing on the next page after I stop this video. What our practice test is and what questions to skip.